Hello everyone, Ashok here. Welcome to another session on time series forecasting. Let me type it down. Time series forecasting. Okay, uh, this is an hands-on tutorial. And before watching these tutorials, it's strongly recommended that you watch the part 1 of this time series tutorial, which has a theory part. Without the theory, this will may not make much sense for you. So I strongly recommend to watch the part 1 before coming here. Alright, in this tutorial, we're going to take a simple time series and try to use all the implement all the theory we learned in the part 1 and understand how time series different model works. Alright, I'm going to use pandas import pandas as PD. If you don't know pandas, you need to watch pandas tutorials also in the YouTube. You can just Google for it. Alright, and pandas is used to import the data. Okay, I'm gonna show you the data which I'm going to use. I have car sales. This is the one. So this contains monthly sales of a number of units of cars. Basically 2016 January, some company has sold about 266 cars, and February 146, so on and so forth. All right, I'm going to import this data by using my read CSV function. Okay, it's in downloads. I have to navigate to downloads, use Ashok, downloads, and sales. All right, super. And just gonna look at it. Excellent. So this is what we had there. We got it here, but we have one problem. This month is really not taken as month. You can see a small quotations here. It is taken as a string. It is not taken as a date. We need to take this as a date. All right. Otherwise, we cannot do time series analysis. So I'm going to import a sub package called date time. All right, just date time. Okay, and okay, and it's better that I define a parser rather than putting directly there the formula. So parser is a simple quick user defined function. I'm going to return saying date time dot. There's a function called stp. I'll take this one from the string to date. This is the same x. It's an argument over here. I'm converting this. I'm basically passing on the format. This is 4-digit year. So I say percentage capital Y, and there is an hyphen, as you can see. And then there's a month, which is 2 digits, which is this is a format. Okay. And I have to tell my pandas function read CSV that use date parser. And now you see that it should be date. Okay, we need to tell which of the columns contains dates. Okay, let me see. There should be a function called pass dates, and then you can, if you have one column, then you can just pass on the 0. If you have multiple columns, you can. Right now I only have one column with dates. If you have multiple columns with dates, I can just put on this date columns here, and this will. Alright, great. So as you can see, now it is timestamp and the dates are converted into proper date format. Python has assumed day as first of every month because there is no day actually in my data. It only has month and year. Fantastic. I also wanted to do one more thing. I want to have this date column as index so that I can do the time series forecasting. So it has to be an index. The date has to be index. How do you do it? There is another parameter in read CSV saying index column is equal to, I can mention which column I want as an index. That's the first column, which is 0 index. Now my month column has become index, and I can go ahead now plot it. For plotting, I need a function from matplotlib as plt. I have to pyplot. Okay. Oh, sorry, import. Okay, and all right. So I got my first graph or trend of my sales of cars. All right, now going back to the theory part, right? stationary. If you watch part 1 of this series, of this tutorial, is it stationary or not, this graph? No, because when you say stationary, I'm going to just write it down over here. Stationary means your mean, variance and covariance is constant over different periods of time. Constant is constant over periods of time, anytime, anywhere, over periods. So what does it mean is, if you take a small period over here, find out a mean, covariance, for example, just mean, and this has to be same as if you find a mean in the same period, same duration of the period over here. Apparently, I can see that they are not same. The mean over here may come around 200 and the mean over here is about 450. So this is really different. That's because my data has trend. There is an increase in sales over a period of time. So as we know, stationarity, actually stationary, okay, stationarity, okay, that's fine. As we know, we have to convert this series into stationary, otherwise we cannot apply any of the time series analysis. Okay, how do you convert this series into stationary? Converting series to stationary. Again, as we have discussed in the previous session, we will take a difference of the series. What is difference of a series? Difference is nothing but taking a consecutive values and finding a difference and making that as a series. For example, this is my value. The new series I'm forming will be a difference of value of this minus this, and this minus this, and this minus this. There is a nice function in pandas which says difference, and I can mention the periods if I am not wrong. Yeah, periods. I'll say one difference. So automatically what it has done is, first number is anyway nan, because it actually differentiates start from the second number. So minus 120 is nothing but 146 minus 266. 37 is 183 minus 146, so on and so forth. Okay, this is a different series. So I'll say this is difference. Okay, excellent. And I can now look at my different series. Okay, and well, I don't like the nan at the top, so I'm going to simply remove that nan. It is disturbing our analysis. So I'll simply say diff, take from the first value to the end. So now my first value is like my nan value is chopped off. Excellent. All right. So we have visually looked at this and said that this is not stationary because there is a trend. But you can also do it using ACF plot, which is also discussed in the previous tutorials. It's called as autocorrelation function. All right. I'm going to use autocorrelation function from stats models, and I guess it's graphics. Yeah, graphics. And then you have plots, TSA plots. And import, it's called as plot, and there'll be a lot of plots and ACF. This is also called as partial ACF, which can be discussed later. So if you look at this ACF plot, I can say sales. All right, this is your ACF plot, and what it shows is, it is showing you the correlation between two series. Well, we only have one series, but this is the correlation between the same series with a time lag. What do you mean by that? It is like this is one series, and the next series is formed by just shifting the time. How do you do it? This is one series, and the next series is something like this. I guess there is also a shift function, if I'm not wrong. Yes, shift. I'll say shift 1. Okay, see, I just shifted this by 1. It went down. The first one actually became a nan, and the January value has came to February, and so on and so forth. Now, if you again set it back, basically remove the first one, and then try to find a correlation between two things, and that is called as autocorrelation. And these are lags. When you correlate sales you get obviously one correlation coefficient, which is this one. When you have one lag, which is the one I showed here, one lag, there is a one time lag, the correlation factor is zero 0.7 kinds, and then two lags is 0.75, and so on. It's slowly decaying. If it is slowly decaying, it is showing that the series is not stationary. Okay, it should be ideally decayed immediately, like it's going to die like this, and the next correlation is either 0 or negative. That shows that your data is stationary, and we need stationary data to do time series forecasting. Okay, so this difference function, I guess, should be what was the plot ACF. Yeah, I can now do the sales for difference. I'll see that it quickly decayed and went to negative, so this is very good stationary. I can also visually look at it. I'll say sales difference dot plot, simple plot, and you can see that there is no trend here. It is stationary. If you more or less, if you look at mean at every point, it is same. Covariance, variance also looks same. All right, this data is good enough for us to go moving further to our modeling. Great. All right, so we have done analysis of, we basically imported the data and looked at the data and made sure that time factor has become an index, a time column data has become an index, and it is recognized as time, right? Then we looked at the plot, we found it is not stationary. We have taken a difference of it and then made it stationary. And also, very important point to note, this is also called as integrated of order 1. It's 1 because we're taking one lag or one time period difference. So one difference or differencing ones is also called as integrated order of 1. Remember, in a ARIMA model, the second term integrated is nothing but this one, and it's typically denoted by D for difference, all right, and this is one of the parameter of ARIMA model, the middle one. ARIMA, R, is nothing but difference, integrated, and that is actually D. Okay, good. Moving forward, now that we have understood the data a bit, and we also made it stationary using some difference function in an isolated manner, now let's go ahead and do some modeling. Okay, and I would like to actually start with a simple autoregressive model. What is autoregressive model? Please watch the first tutorial, right? And that is also from stat package. I'm going to import stats models, and this should be in STA, not STA, and AR model. Okay, good. Import AR. Okay, that is the function model I'm importing. I will also import my mean square from sklearn metrics, mean squared error, because I can find out the error actual. You know what is mean squared error, right? You'll find the error, square it, add it, and find an average. That's mean squared error. Okay, so this is like any other. Before that, let me actually divide. If you're following my previous tutorial in machine learning, so you should be able to understand what I'm saying. We normally divide this data into two parts, train and test data. So I'm going to do that as well. Here we don't have x and y, we simply have x. So I'll say sales.values, and then you can look at my x. So this is my x. X is nothing but a lot of sales data. All right, and then let me see the size of the x. No, that doesn't work. It's capital X. So yeah, 36 data. Of course, we have 3 years data, so 3 into 12 months each, so 36 data. Very nice. And I can manually break it. So I'm going to simply say train is equal to x of I'm going to take 90% of the data, or 80% of the data for training and 20% for testing. So 80% of this data will actually become about, let's say, 27. So from 0 to 27, I'll take it as training, and test, I'm going to take it from 27 till the end, whatever it is. Is it good enough? So I can also use a generic functions like you can find out the size and do it, but right now I'm going to do it in a very rudimentary manner so that you don't get confused. So I have 27 readings as train and remaining how many? About 9 into testing. Okay, good. I'm also going to define a quick list called as predictions. So because I'm going to predict using AR model and then ARIMA model. Okay. So this is basically 9 data to test and then 26 or 27 data as train. Let's say train data and test data. Okay, good. All right. So after I split this, now I'm going to initiate a model called I'll just call it as model. I'll just say model underscore AR, and I'll say AR, and I'll pass on the train data. Okay. And then I call the fit function dot fit. I can actually say fit because it will give you an object called fit, so it is slightly different from your other things. Okay, there's some problem. Model is not defined. Where is model? Oh, sorry, this is underscore AR. Okay, so I have trained my forecasting model now. Now I can predict. I can simply predict by using a predict function. I can say model dot, okay, what is that? Model underscore AR underscore fit. That's the train model, and say dot predict. I guess predict. Yeah, good. And I can give the starting and ending point for predictions. Okay, so I can simply say start. I think that's the parameters. So we have start, end, and that's the only two things I'm interested. Dynamic is anyway false. So all right, start. I'm going to say I will start at 26. Let's just start at 26 and 26 or 27, and I'll end at the last data, which is 36. I guess 36. Okay, that gives me the predictions. I already have test. All right, so this is the test. Test is the one which is like last 9 data, and this is also 9, isn't it? 1 2 3 4 8 9 10. So I'll just make it 28. Oh, that's weird. Yeah, that's true. Okay, why I'm getting 10 here? I'm supposed to get, how many data we have? Okay, 27 and then 36. So this has to be 28 and then 28. Otherwise it will become no. Okay, so this is the reason we actually write it in a general format, but nevertheless this is my test and this is my predictions. I could simply plot this two and see how it looks like. I'll simply say plt plot, and I plot my test data. So this is my test data, which is the actual data, and I'm gonna plot my predictions now. Predictions, oh sorry, plot predictions. No, apparently there is no predictions. Color is equal to red. Okay. Oh, I did not store it. I'll say predictions is equal to this. Okay. All right. So I see that we are at the same levels. The actual graph, if you look at it, I'll also plot the actual graph just for a reference. So the actual, these are the readings I'm looking at, because I have taken the last 9 readings. So these are the last 9 readings. So this part of the graph from here to here is actually the blue color over here, and then I have AR, which has predicted something like this, which is kind of okay. But remember, we haven't really did anything with stationarity. I can see the effect because the values are a bit lower side, because the trend is not being really taken care. And this is one of the models, and this is a very simple autoregressive model, which will find it will actually, like linear regression, it will take few values at the back, and accordingly it will extrapolate or regress and predict the future values. Okay. I think there's a slight shift on here. I think the graph should be shifted, and that is coming because of yeah, this looks more correct, that the pattern is correct. Okay, good. But let's quickly move on to the next model. I'll just name this as, because I'm going to share this file after this session is done. So I'll just name this model as auto regressive or AR model, a simple AR model. Okay. We can also do a MA model in a very similar manner. There is a function called MA in stat models, but let's directly go into the ARIMA model. That is the main topic, ARIMA model. ARIMA model is a combination of 3 techniques, which is autoregressive, integrated, and moving average. Okay, and ARIMA model also we have it in stats package. So I can simply write something like from stats models, yes, and again the TSA, yes, that's and then ARIMA, I guess, AR model, yeah, ARIMA model. I'll import, there is a function called ARIMA, if I'm not wrong. Yeah, that's correct. So I import this. The train and test sets remain the same. There we have used AR. Here we're going to use, I'll just call this model as ARIMA, just to differentiate, because we're doing both the things in the same sheet. And I'll say ARIMA, and I'll pass on the train. All right. Unlike your AR, which automatically finds everything, ARIMA, you really need to specify the parameters. What are the parameters? There are 3 parameters in ARIMA: P, D, and Q. P is periods taken for auto regressive model. So it is like how many months it is like if I want to predict my my June sales in 2017, am I taking May and predict June, or am I taking April, May, or predicting? If I'm taking only May, then you're taking 1 period. If I'm taking April, May, then I'm taking 2 period. If I'm taking all the entire 6 months or 5 months behind June, I'm taking 5 periods. This P indicates a number of time units you're taking previously for regression, so that we are taking 6 points or 4 points to find out the current regression value. This has been clearly explained in the previous tutorials. You can refer that. And D, I just explained you. D is nothing but an order of integrated order, or simply how many times differencing is done. Typically 1 or 2 is a good value for this. And Q is your moving average. It's very similar to what we have done with P in autoregression. In moving average, we are taking errors rather than the past time. So Q all indicates the number of periods in moving average. Periods, lag, periods in moving average model. Excellent. So we have to mention this order in that fashion. So I have to say PQA. So if I say, let's say 1, 1, 1, 1, that means 1P, 1D, and 1Q. I'm taking 1 period for autoregression, 1 period for moving average, and 1 period for integrated order, differencing ones. Okay, excellent. And in a similar manner, after that we going to do a fit. I'll say ARIMA underscore fit. I'll say call the model ARIMA, and I'll say fit. That's all. I'm gonna simply run it. There was some error. Inverting failed. I don't have to be concerned. It's a warning actually. Okay. Okay, we will see. Okay, good. I'm going to do the predictions in a very similar manner I have done before. Prediction model ARIMA fit, and then I pass on. So here in ARIMA, you can pass a number of steps in a very similar manner what I've done. So I'm going to say I want to predict 9 values. Okay. And if you look at the prediction, it gives you an array. Okay, what happened? Object is not callable. Oh, there's something went wrong. Train data. Okay, so I'm using the same train data. So train is about 0 to 26, and then 4 plus. Okay, 0 to 26. I have to say 0 to 20. I want to take 9 values for testing. So there are 36 data. So up to 27, I can take it over here, and from 28 till here, we'll take it in the test data. And let me see if I have. No, it's only 8 we are getting. So how many data we have? 36, isn't it? So X size, yeah, 36. So 0 to 27, yeah, that becomes correct. I haven't done anything wrong. So, and test data size is 9, and the train data size is 27, which is what I wanted. Okay, and oh, maybe there is a problem with the values here. So I'll put 3. Yeah, so not all the PDQ values are correct, because obviously it is trying to use 3 different techniques, so there are conflicts, and it's very difficult to explain the conflict. So we will just go ahead with it. So let me just do the predictions now. Okay, it's not callable. Predictions. Okay, so model underscore ARIMA fit dot forecast. My apologies. So there is a function called forecast, right? So it just went okay, good. So there's a big array it gives. I'm interested in only the values, so I'll take the first part of it. These are the predicted values. It is very similar to your AR model, where you simply call it as predict, and in ARIMA model we call it as forecast, but more or less does the same thing. So I'm forecasting 9 values because my test size is also 9, so I can plot both and see. And I can do the similar thing what I've done over here. So I'm going to simply plot these 2 things and look at how it looks. Yeah, it looks better than that, but how do you get the best fit? In ARIMA model, we are combining 3 techniques, and it's very difficult to say which parameters of PDQ will actually work better. There is a one method we use, which is AIC method. In the theory, I have explained briefly about AIC, which is what you have to remember is we should go for the minimum value of AIC. It's more like your mean squared error. Okay, so I could simply print my AIC value. I can say print AIC value. So in this case, I have 295 as an AIC value, which is pretty good. I can see a good graph, but there is one shifting, as I can see over here. Why it is shifted once? Okay. Training is done, and then testing is actually I can see there is a one shift. Okay, so let me just go ahead and take from 26. Yeah. Yeah, this looks correct. So I can do a forecasting of 10 values to make it more look nice. Okay, good. So this is your red is your prediction through IRMA, ARIMA, IRMA model, and the blue one is there's a lot of things possible, and this value AIC value is 295. We have to prefer the minimum one. We can actually go and do the trial and error and try to find different ranges. So I can actually make this as 0 now and see if it is not throwing any error. So I got lesser value C, so there should be a better model. So I think it is actually moving up. Very good. I can increase this. I can make it 4, which is your p-value. Sorry, p-value, which is a number of periods you're taking in autoregressive model. Oh, it came back to the normal, so I don't see it's correct. So you can play with it and find it, but you can also do it using a simple for loop. Okay, let's just define our p is equal to d is equal to q is equal to range of 0 and 5. So I'm going to give you all the values, all the 0 to 5 values for PDQ. Some of the combinations might not be correct and ARIMA might throw error that we will handle. And after that, I want to create a list which basically have all the combinations of this PDQ. I'll call it as PDQ itself. And the list can be created by using a simple tool called I'll import iteration tools. Yeah, it's a very nice package, a lot of help, and I'm going to convert this into a list. I'll say iteration tools. I'll take a product, basically combines all the combinations that is product, and I'll pass on PDQ. All right, and then if you look at this generates a list which contains these values. See, these are in a same format as what you've given, but it has all the combinations 0, 0, 0, 0, 0, 1, 2, 3, 4, and then all the combinations. Okay, rather than trying manually all these things, what I'm going to do is I'm going to simply put a for loop and say parameter in PDQ. So each of this parameter, each of the one value in the parameter will be taken in param variable, and then I can do the modeling here just like I have done it ARIMA. I'll copy paste it. I don't have to type it again. I'll do the same thing. Okay, but here I'll just put param. So what happens? It goes through each and every combination and tries to give you AIC value, AIC criterion. It has thrown an error because not every value is correct, because it doesn't like all these values. Sometimes the values are conflicting. They don't make sense. So it throws error. We can use simply a try block. I'll say try, and if there is an error, it calls exception handling. If you're not from software background, you don't have to worry. You just accept and continue. So you just put these 2 sentences. It will keep on running without stopping, and it is still running, but there are errors as well. I'll just try to also handle that. Let it complete first. Is it complete? Yeah, it seems so. So the errors doesn't look fine, so I'll simply say import warnings, yeah, warnings, and I'll say warnings, I guess. What is it? Filter warnings? No, I don't have it. So it should be warnings. Yep, dot filter warnings. Yep, this one. And then I can say ignore. Now I only have AIC values being coming up. I can just leave it like this and see which combination is giving me minimum value. I can already look at, yeah, there is something which is minimum over here. I don't know which combination is it, so my apologies. I need to also print down the param and then that. Then I know, okay, these are the combinations giving me these values. I can also put collect all these things and find maximum value and all this stuff. I'm showing you to do for your more clarity, and of course we can obviously make this piece of code more better. I see that the minimum combination actually coming from here. See, 291. So I'll take this 291, I'll put it here, and look at my graphs. Visually it doesn't look so accurate, but based on AIC it is. But let me also try, because I restricted that to 5. I think there are time lags is actually 9. I can also get it from different. Okay, let me try my own models. I can this. Okay, I put moving average 0. Yeah, this looks even better, isn't it? Okay, I can also reduce it to 1 and see if that gives you better value visually. Okay, you can play with it, and this is basically ARIMA model. So this one model which allows you to combine the 3 techniques, which is autoregressive, moving average, and integration, right? If when you put 2 here, you're doing differencing 2 times, right? And you can play with this. We can also use mean squared error to calculate the error between predictions and test. How do you calculate the error? It is quite simple. I'll use mean squared error. I'll pass on the test and predictions, and it has given me a mean squared error. So this has to be minimum. So we can make it minimum by fine-tuning these parameters. And one of the way we fine-tune is like kind of generating this all combinations using this small piece of code, and and running a small if loop and printing it and visually watching it, or you can just store it in a list and find out the minimum value. I can visually find this as a minimum, but I also played a little bit with it. I put a 9 because I think 9 months is kind of like, I look at the graph, it looks like more or less it has a pattern repeating in 9 or 10 months or so. I put 9 because my test values is actually maximum 9, right? And it has given me even better results visually. Okay, this is auto-regressive, and this is your ARIMA. So ARIMA has a little better when compared to okay, let me put 10, but I'm pretty sure it's gonna throw error. I didn't. Now it is falling apart. I'll put this 2. Okay, I think 9.2 seems to be good for me visually, but of course I can extend my AIC loop and find out which is best. Okay, so this explains your AR model, MA model, and ARIMA model and integration. So this is a complete knowledge you need, and anything further is basically playing with the numbers and trying to get the best fit. Hope this tutorial is helpful, and if you have any questions, comments, please write it down in the comments. I can record another video with more clarifications, right? I'll share this file to you as well for your reference. Thank you for watching. Have a great day.